So yes, as the organizer, I'm given the honor to give the first talk here, and also to introduce our department here at UNIST. So me, in fact, I in fact joined the university here in August 2021 as an assistant professor at the Department of Mathematical Sciences. And the department here is subdivided into three major groups. The first group in pure mathematics is the number theory group, where we have three professors here working on research topics in number theory. Then in pure mathematics, we have also the analysis and PD group, where we have five professors working on various topics in analysis, PD, and also various computational methods of solving PDEs. And then last but not least, we have professors working on applied mathematics topics, ranging from mathematical finance to computational mathematics, various dynamical systems, and also image analysis, mathematical biology, and when I joined also on mathematical physics topics, ranging from string theory, quantum field theory, and mathematical physics. So in fact, before I joined in 2021, I first met Professor Yao when I gave a seminar at the CMSA in Harvard in 2016. And the topic of the seminar that I gave was on brains and 2D zero-2 theories, mainly a string theory topic where I used various tools from geometry to construct large classes of 2D zero-2 theories. In fact, I gave a talk where we talked about the class of 2D zero-2 theories that I realized as word volume theories of some D1 brains that probe a class of toric Calabi-Yau fourfolds. So that forms a very particular class of 2D zero-2 theories with very interesting moduli spaces. And the nickname that we gave to this class of 2D zero-2 theories was what we called BrainLink models, because the string theory realization of these class of 2D zero-2 theories was a certain brain configuration that forms a tessellation of free torus. That's precisely what we called as the BrainLink model. The interior of this tessellation is somehow a D4 brane that is suspended between a certain NS5 brane that wraps a free torus, and the wrapping of the free torus forms various tessellations that encode the geometry of the corresponding toric Calabi-Yau fourfold. So that was actually the topic of the seminar that I gave in Harvard in 2016. And Professor Yao got quite interested, and he looked at these pictures. And at some point, we had a discussion in his office in Harvard about toric varieties in general. And in fact, given a toric diagram and its corresponding toric variety, you can associate it on one hand to the non-compact toric Calabi-Yau cone over that variety. That gives you something which is one dimension higher than the dimension of the toric diagram. But you can also associate it to a compact smooth Calabi-Yau, which you can think of as the hypersurface over that corresponding toric variety. So we looked at, had a discussion on the differences between the two. And one thing that was quite interesting was Professor Yao himself in 2006 wrote a paper with Martelli and Sparks, where he wrote down the methodology of computing the volume function of the associated Sasaki-Einstein manifolds that relate to the non-compact Calabi-Yaus that you can associate to a class of toric varieties. And in fact, these volume functions have a unique minimum, and that minimum of that volume function can be considered as a geometric invariant of the corresponding toric Calabi-Yau. But on the compact side, you also have our common geometric invariants, for instance, the Chern number or the Euler number of the corresponding variety. So with his insights, Professor Yao asked whether there is a correspondence between the minimum volume and some of these geometric invariants. So that was the question that he gave me, and we went back, and with with one of my collaborators, Yang Hui He, we ended up writing a paper on the relationships that we found for the minimum volumes and the corresponding Chern numbers and Euler numbers of the various Calabi-Yau manifolds that you can construct for a given class of toric varieties. In fact, we looked at a certain class of toric variety where the toric diagram is formed by a reflexive polytope. So reflexive polytopes are convex lattice polytopes that the polytope has only a single interior point, which is the origin. So Kreutzer and Skarke classified these polytopes in various dimensions. In fact, in 2 dimensions, there are exactly 16 invariant convex lattice polytopes that are reflexive. And in fact, in dimension 3, there are over 4,000 of them. And amongst those 4,000, 18 of them are considered to be so-called regular reflexive polytopes in dimension 3. In fact, the classification goes on to dimension 4 and 5 as well. But for dimension 2 and in the particular case of dimension 3, these corresponding varieties correspond to Fano threefolds. So in this particular paper with Professor Yao, we computed the minimum volumes of all those non-compact Calabi-Yau threefolds that are associated to these reflexive polytopes in dimension 2, 3, and 4. And we then mapped the corresponding Chern numbers and Hodge numbers of the associated compact Calabi-Yaus. And what we found was that the minimum volumes of the associated Calabi-Yaus have a lower bound as well as an upper bound that is classified and characterized by the Chern number and Euler number of the associated toric varieties, which was very nice, and we were able to write down equations in terms of these invariants for the lower and upper bounds. But in fact, as a follow-up of this project, nicely enough, is that in fact, we ended up computing thousands of minimum volumes using the prescribed protocol from Martelli, Sparks, and Yau's paper, computing the equivariant index. From there, we have to use a limit to compute the corresponding volume function. Then, using the volume function, you have to find the global minimum. So there were various steps, and you can do that for every toric variety and compute the corresponding minimum volumes using that procedure. But after doing that a few hundred times, you think yourself that there must be a better way to do this computation. And during a visit to CERN, I met my friend Daniel Krefel, and we ended up writing a paper where we proposed using machine learning in 2016 to compute these minimum volumes using machine learning. So that was actually the first time where a proposal was made to use machine learning techniques to go around techniques in mathematics to compute certain quantities that are important both in mathematics as well as in string theory. So here in this paper, we ended up writing down various different machine learning models, including this twin model, where on one side you have a regression model, on the other side you have a convolutional neural network, and the input is given by the toric data of the corresponding toric variety, where you can cook up various integer numbers depending on how many corner points, how many internal points the corresponding toric diagram can have, and you can cook up various features that then you can include into a candidate formula, which is shown here. And this candidate formula is then evaluated by the machine learning model, and the weights of this formula, the coefficients of the formulas are learned by the machine learning model, and the output is a resulting function that approximates the output minimum volume of the Calabi-Yau in terms of various other geometric invariants that you can derive from the corresponding toric variety. So yeah, interesting enough, such machine learned formula for the minimum volume of the Calabi-Yau achieved an accuracy of up to 0.9%, which is even better than some numerical computations that have been done before. So more recently, last year, we improved this project that we did 5 years ago with my student Eugene Tse. And in this particular paper, we pushed the machine learning model. Here you can see some plots where on the first column, you see each of these curves are potential candidate variables that can contribute to the formula of the Calabi-Yau volume. And you can see that when the model is trained further, then certain candidates die off, and you can then obtain an optimal selection of candidate parameters for the formula, which minimizes the number of variables in my candidate formula for the minimum volume, but maximizes the loss of the approximation. So you can actually keep track of how the machine learning model generates formulas that approximate geometric invariants for a given toric Calabi-Yau threefold, in this case, the minimum volume. And at the end, you end up with these explicit expressions of polynomials that approximate the minimum volume with an accuracy up to 0.99%, which is like an error less than 0.5%, which is very much. And you can achieve this with just 3 integer numbers that you can cook up from the corresponding toric variety. More recently, I looked also into other ways how machine learning can be introduced to study these toric Calabi-Yau threefolds, in particular in terms of the mirror description of the Calabi-Yau. So every toric Calabi-Yau has its mirror. And I can describe the corresponding mirror in terms of the corresponding mirror curve, which you can obtain from the Newton polynomial of the corresponding toric diagram. It's a polynomial which counts the vertices of the points in the toric diagram, and the coefficients of this polynomial correspond to complex structure moduli of the corresponding Calabi-Yau mirror. Interesting enough, using when the polynomial is equal to 0, this polynomial determines a homomorphic surface or a curve, depending on the dimension. And this surface or curve can be projected using topical geometry either to the amoeba curve or the co-amoeba curve. If you project it to the co-amoeba curve, meaning if you project the complex coordinates onto the angular parameters, in the case of toric Calabi-Yau threefolds, you would have then 2 angular parameters. The co-amoeba would then be a projection onto a 2 torus, which looks like this. And this is an example of the Hirzebruch F0 surface. It has 4 terms in the polynomial, and we have 2 complex structure moduli. If you end up changing the complex structure moduli, you can see how the co-amoeba curve for the given Calabi-Yau changes, right? And the question now is, at some point when you change the complex structure moduli, the co-amoeba ends up undergoing certain transitions from one geometric phase to another geometric phase. In the string theory interpretation, these geometric transitions correspond to dualities of the corresponding quantum field theories. And the question that I wanted to ask was, where are these transition points in terms of the complex structure moduli? Can we identify the boundary values in terms of the complex structure moduli where these phase transitions appear? Obviously, now having 2 complex structure moduli, which give you in total 4 real parameters, you can end up searching the 4-dimensional space for those boundaries, but that would require you to do many computations of the corresponding core amoeba for a given value of the complex structure moduli. But ideally, now using machine learning, you can do this fairly easily, where now you can generate many of these core amoeba for various choices of the complex structure moduli. And then you can use something called principal component analysis in machine learning that dimensionally reduces this data set of core amoeba to just a two-dimensional phase diagram, where each of these points in this two-dimensional phase diagram correspond to a particular choice in the complex structure moduli and a particular instance of the core amoeba projection of the corresponding Calabi-Yau freeform. And the result is a figure like this, where every point corresponds to a choice of complex structure moduli. And now you can see that this diagram is basically a geometric phase diagram, where on one side you have points that are parameterized in terms of certain values of the principal components that come from the complex structure moduli associated to the core amoeba projections. And on the other side, you have the other points that will correspond to other instances of the same geometry, but in terms of different values of the complex structure moduli. In fact, if you use more advanced machine learning methods, this becomes even more clearer. You can now cluster these points, which are now sets of complex structure moduli with different core amoebas associated to them. And these clusters now can be identified to precisely different phases of the same Calabi-Yau geometry, but at different values of the complex structure moduli. In fact, the machine learning model can identify at what values of the complex structure moduli these phase transitions appear. And now these phase transitions in terms of string theory then relate back to where the Seiberg duality transition appears in the corresponding quantum field view. So this is an example done on the cone over F0 model, which is basically P1 times P1. But obviously, you can do this same game for more complicated toric Calabi-Yau freefolds, or even higher dimensional Calabi-Yau freefolds. So in fact, you can play this game in string theory up to Calabi-Yau 5-folds, where you can probe these Calabi-Yaus with various different branes of different dimensions. For the case of Calabi-Yau 3-folds, when I probe them with the 3 branes, the world volumes are 4-dimensional. When I have Calabi-Yau 4-folds, I can probe them with the 1 branes, where the world volume is a 2-dimensional theory. And for Calabi-Yau 5-folds, the world volume theory is a 0-dimensional matrix model. And in these different cases, all these geometric transitions appear, and we can now study with machine learning models where these geometric transitions appear, and then give them a physical interpretation in terms of dualities that appear in the corresponding quantum field fields in terms of the corresponding supersymmetric gauge fields. Interesting enough, for Calabi-Yau 3-folds, the duality is known to be what is known as Seiberg duality. In Calabi-Yau 4 case, the geometric transitions correspond to not a duality, but what we in string theory call a triality of 3 different 2D 0,2 theories mapped into each other by a period 3 identification. And in the Calabi-Yau 5 case, with Kumon Wafa and collaborators, we identified that the corresponding transition corresponds to a quadrility of 4 different 0-dimensional supersymmetric gauge theories identified by a period 4 identification. So the goal is to use now machine learning to really map these dualities, trialities, and quadrilaties in quantum field theory with geometric transitions in the context of Calabi-Yau 3, 4, and 5. I think with that, let me welcome again Professor Shing-Tung here to Korea. I think your last visit was in 2018, and it's a great pleasure to have you here, and also all the other international and domestic participants. Welcome to UNIST, and I hope in the next 3 days we will have a very productive and also very relaxing discussion session. And I hope you enjoyed your time here in UNIST. Thank you very much.